Thank you very much for coming. It's a huge pleasure and honour to be here. I'm going to try and tell you a story which has been anticipated quite accurately by Martin, I think, because it's a story between pure mathematics and applied mathematics. So I think mathematics is really about building a language, convenient language that other people can use, and there's lots of evidence it can change the way we do things. This story particularly is about the language of evolving systems, streams, and that in a sense is a real world concept, and we're going to try and link it to a mathematical concept, which is that of a signature. And this story is dedicated very much to the critical contributors to this project, my family and my co-workers being primary in this. So thank you very much to them. We all understand, I think, that number is something quite clever. Why is it clever? Well, somehow it's because it detaches from the context. On the one hand, if you talk about 3, you lose a great deal compared with what you might actually see. That 5, the 5 fingers, doesn't really tell you what's going on in this picture, but it's still very, very much a concept, and from a very early age, children really do learn to understand that you can have 5 fingers, 5 toes. We teach them this and then go on to everything else. What I find remarkable is that actually from those very abstract idea that you could go from there to being something similar between 5 beads and 5 fingers, you end up with something really quite solid. And even 1800 BC, people were doing things with numbers. They were writing down Pythagorean triplets and so on. They grow from these abstract ideas, rich models, castles if you like, that end up enabling us to do much more than we thought we could do just by counting with our fingers. And I want to try and tell you about another story, actually another object that I think we really are very familiar with day by day, just like counting, that has also got an abstract content to it. It carries the same warning that understanding the abstract concept doesn't tell you very much, any more than understanding 3 tells you very much about, or 5 tells you very much about that child. But nonetheless, it's very powerful, and it can be used to say powerful things. So the thing I want to talk about today is a stream, just a sequence of events happening with some sort of time stamping, typically multi-channel, so not just a series of numbers changing, but actual events happening. And what I'm going to try and persuade you in this talk is 2 primary things. One is that there really is a mathematical theory to think about, and the other one is that there really are many, many instances of these objects which do not have the same context. And they're a rich set of objects. They're a rich mathematical set of objects, I think probably much richer than numbers, in fact, although you probably need numbers to study them. So that's what it's about, okay? I want to tell you about streams, and mentally I want you to think of those as real-world objects. And at the same time, I'm going to talk about maths, and the maths is sort of going to come from the signatures. We're going to have to rush quite quickly to get remotely through this picture, because it's quite a big picture. But if we start with some very simple streams, so this video is a stream on 2 levels. At the one hand, it's a picture evolving, so that's like a million-dimensional stream or something, however many pixels there are, but you can distill from it, using expert knowledge, lower-dimensional ones, and one of my postdocs has, which actually translate this into, for example, that there's a car, the car moves in, it's got such and such a position. These tend to be much more useful, use expert knowledge to distill it down to something of moderate dimension. But it's obviously quite an important sort of problem, and clearly you can distill down some abstract streams, such as you see on the right-hand side. And now what about the sort of questions you can ask? Well, this is where it gets interesting. You see, I think the real world is very interested in understanding how to say something from looking at these objects. In other words, in mathematical language, they're interested in functions on streams. The function we're trying to study here, actually, is can you go from the TfL data that this is representing, looking at the various road junctions in London, to the levels of nitrous oxide pollution? And that's the particular question that we're trying to do here with my colleague, Mohammed Ibrahimi. So let me go back to the maths, and in 2014 was an exciting year, actually. I was giving a talk at the International Congress in Korea, and explaining for the first time, I think, really the connection we had identified properly between the maths of rough path theory and data science, and that was what my talk was about. At the same time, applications were happening for the first time. Just before that, Ben Graham, who was then a lecturer in Warwick, had been able to put it to rough path theory and signatures together with new things from neural nets and deep learning, which were very new at that time, to achieve state-of-the-art in recognizing Chinese handwriting. At the same time, Martin Heira was using rough path theory to do, and building on it, regularity structures. And those regularity structures did amazing things with stochastic partial differential equations. It doesn't matter much in this context. We don't have time to go into it, but it's an amazing and deep contribution. Martin got a Fields Medal at that Congress, and that was very exciting, and I think I was chair of the session when he spoke or something. It was very exciting. Since then, he's gone on to get the Breakthrough Prize in Mathematics, and there's Martin there. And but the range of applications is quite broad. As I tried to explain at the beginning, perhaps one interesting example of a stream of data is related to a human being and perhaps to their health. And there are lots of variations on that, but one quite viable one is their health record is, for example, when they're in an intensive care unit. And then you might want to know things like, is there some risk that this patient is going to deteriorate in the next few hours? That's a function on paths. And it's a function to be best driven by evidence. You know, you really do want to know that if these things have happened before, you're able to take them into account. But streams also happen in finance. They happen almost everywhere. And I'll make some more lists later on. The signature of a stream is an altogether more complicated object, and it's a math object, and it's deep enough that I think is worthy of study. And not just it, but the framework it introduces. And we'll come back to that later. But putting these signatures together, I've told you about Ben Graham, and he won competitions and so on, and that led on to it being used commercially, eventually. James Merrill, a little later, led a team to try and identify the occurrence of sepsis using that intensive care unit information. So by using vital signs and everything, can you predict how early can you give warning that somebody might be getting sepsis? And there was a competition, there's an annual competition in using data in medicine called PhysioNet. In 2019, that was the subject of it, and James's team was placed first. James was one of my students. The signature vectorizes, whatever that means, but it vectorizes a stream. That means that, for example, if you have a random stream, or more likely an ensemble of different streams, an experience of how lots of people behave, then you can take its expectation, because it's a vector. And because you can take its expectation, it turns out this expectation is meaningful. It allows you to describe clouds of paths, not particles. This is very powerful too. And it allows you to look at data and discriminate between data. Is it actually really like this set of data or not? And putting those sorts of ideas together, you can build better models for synthesizing financial data. Hans Buller, who at that time was a senior figure in JP Morgan, and now, funnily enough, but by coincidence, is the deputy CEO of XTX that's funding this talk. Mind you, I never got any money, so I don't know where the funding went or came from, but anyway. He actually leveraged this to train his deep hedging models and was recognized as Quant of the Year for doing this with the synthetic data generated by the signatures. It produces a framework where we take our stream and embed it in math. We actually take the stream and we embed it in a group-like element in a tensor algebra. We actually take this collection of streams and embed it as an element of the tensor algebra. And we'll see later that this is not the way you normally think about these things. But it turns out to be practical and useful. And I'm not going to go through what these terms mean. All you might be interested in is it does generate mathematics and interesting mathematics, and actually really quite pure mathematics. So this slide is just meant to give you some idea of the variety of things you can use as streams, and perhaps also to tell you a few of the generic questions that people find interesting across all these sorts of examples, where the generic methods that use the math could be useful. I've told you about the character drawn on the screen or the order book in a market, but it could be a piece of text, it could be progression through a hospital record, it could be astronomical data, so many different things. Ensembles turn up an awful lot too, where what you see is a cloud of different behaviors and you would like to do something with the cloud. And some very basic questions are really about predicting or understanding or identifying what is unusual in this data. And we'll look at some examples later on if I keep this thing fairly tightly paced. I have a slide here for the mathematicians. I'll leave it up for 30 seconds, but I'm not going to talk about it. The question I want to ask you is, what would be an abstract way, but an informative way, to describe a complex evolving stream? Well, it turns out that the answer is really in calculus and in differential equations. In many ways, goes right back to Newton. Newton wrote an important monograph explaining what I would call a controlled differential equation. For him, it was very much about writing down mathematical models that allowed action at a distance. The way that things over here could affect the evolution of things over here. But mathematically, it's essentially describing controlled differential equations. And I'm going to write these controlled differential equations in this way. You don't really need to understand what they are, but you'll see them over and over again. But basically, a controlled differential equation, this is going to be the control. Later on, it might be called gamma. But this is the control. This is the thing that's changing. It's our stream. Then crucially, there's a second behavior, the effect of the control. And this is the real key thing. We're going to understand streams of data by looking at their effects. We're not going to draw pretty pictures of them, which is actually the classical Kolmogorov approach to describing paths or functions. Say where it is at times. That's not what you do. you look at the effects of this stream of information on systems, and this is the mathematical model for that. The changes in the y are affected by the changes in the x, but they're also affected by where you are. And the different f's are different physicses, if you like. Well, Newton understood this and worked it out. But for him, the control, the stream, if you like, needed to be quite smooth. And he introduced calculus to deal with it. Well, today, we turn that perspective on its head. We don't say that if we've got this smooth path, then we know what's going to happen, although that will be true. What we say is we've got this complicated data, and we can understand it better by seeing what it does, seeing what its effect is, what happens when it rolls its way out into the system. You see, let's look at this picture if I can make it work. It's a bit too fast because it was written by Matthew Byrne, who was a student of mine in, I think, 2004. And the computers have got faster since then. So it doesn't roll nicely and slowly as it used to. But the idea here is that you have a path, a stream, if you like, a complicated stream that oscillates all over the place. And what's happening, in fact, is you're looking at a ball that's rolling along that path. And you see, as it rolls along the path, it doesn't slip, it's a football, and the actual rotation that happens gives you some information about the path. Change the radius of the ball, you get different information about the path. And now that's a very simplified model, but it's absolutely at the heart of the thing. Because I didn't need any calculus to see that physical system and its response. It's built in. If these things make sense, they have effects. And the idea is that you should understand those effects. People in dynamical systems call these reservoir computing, and they use it quite a lot. Where we differ from that is instead of taking a black box, a random box, and crossing fingers and hoping for the best, instead we choose a white box. We choose a very careful nonlinear system. And that very careful nonlinear system solves one of these controlled differential equations, but a very simple one. It actually generates the exponential function, but a totally non-commutative exponential function. And the solution lives in something which the algebraists here will know about. It lives in the tensor algebra over the original space spanned by the channels. And so that's actually quite mathematical. You're going from this complicated segment of hospital data into an element in the tensor algebra. And it's not surprising in a way that people have put a lot of thought into the mathematics, and by leveraging that thought, you can do some interesting things. The first paper really, as I said, was in 2013. This is just before the Congress, where we basically laid out a pattern of how you could use these things. And particularly Daniel Levin and Hal Nee, who were young early career scientists at the time, played an important part. Yeah. But in doing this, I think we've really changed, well, not we, but the game has changed. You see, every one of these little curves is actually an element in the tensor algebra. The ones on the left are paths, so they end up in the group-like elements. The ones on the right are trees, and you can think of a tree as a collection of paths back to the root, and you can average them. And so you can actually represent that as an element of the tensor algebra, but not as a group-like element. And the point is that this gives you a handle on the space of functions on the trees, on the paths, on the streams. And believe it or not, people are really very interested in functions on streams. They really care, right? Because what does it mean? A function on a stream is, a stream could be something like our health data. The function could be one if you have cancer and 0 if you don't, then actually people care. And the data you're looking at is actually quite complicated. At the moment, we tend to let human beings do it, but sometimes they can't cope. And sometimes we can help and do better. So I think we're really doing something quite interesting here. So the left-hand side is actually data from an intensive care unit. It's the vital signs of somebody drawn from the MIMIC3 database. And the right-hand side is actually the evolution of people's self-reported mood, plotted a coordinate against a coordinate. So there are 6 moods, and you look at the evolution altogether, and you begin to see there's quite a complicated pattern, and it would be good to be able to describe it. In fact, using the signatures, you can do quite well. It's natural to ask, well, so what? Why can't we dream something else up? What's signatures special about? We've seen a hint of that because I've already told you that the map from the stream to the maths takes you to something we recognize, we understand, has structure. So it'd be quite surprising, actually, if it didn't give you something. And I'm going to try and explain to you the somethings. The first thing, actually, which I'll explain before I really start talking about it, is I will use the word algebra, and most of you won't care, but the few of you who know what an algebra is might be interested to realize that this map is a homomorphism. If we take 2 pieces of stream and join them together, then the signature of the join is actually the product of the signatures of the individual pieces. Moreover, if you run it backwards, you get the inverse. But the core mathematical idea that makes this sensible is that there's something really difficult about stream data. And the thing that's really difficult is actually the dimensionality. The trouble is, if you have a multi-dimensional stream and you observe it for several steps, and you're interested in, say, does something happen on channel A before channel B, you could probably do that, and it'll be some sort of quadratic function. But if you try to learn relationships from the data, it's horrendous, because the number of quadratic functions, the dimension of this space, is quadratic in the length of the data set. And if you have 700 slots, then 700 squared is a big number. And if it involves 3 things, it's cubic. The result is that actually there's a huge dimensionality blowing up there, which in practice means that you can't learn things from data. There just isn't enough of it. There are ways around it, so I'm overstating the case. But that is a basic perspective. And another way of putting that is that data science hates symmetry. Symmetry is something beautiful normally. It's telling you that there are different ways to look at something which have the same meaning. What that actually means in data terms is you have different representations of the object, and they all mean the same. And if you're trying to learn this from data, that's really bad news, because you've got to look over and over again at a vast number of different variations before you can learn that they were really the same. So by and large, if there's a symmetry, this is something the mathematician needs to feed in, not the data. And this is actually one of the points. You see, something like this 3, I could write it as, if it was drawing it, I could represent it as 2 time series. So that's actually what's going on here. That and that correspond to drawing it. But so does this and this. Well, the only difference between the 2 is the speed at which I move the pen. And they produce completely different time series. And the data science is meant to learn that they're the same. There's an enormous number of streams in this world where you don't care about the sampling rate. You really don't care whether your movie is at 50 frames a second or 60 frames a second. You really don't care when you're measuring the temperature whether it's measured once per second or once every half a second. But actually, if you view it as a time series, this causes you big problems. The strength of the signature is that because it's a differential equation, that differential equation has an invariance. If we go along the control faster, we simply go along the response faster. So the signature and those control differential equations, if we look at our path, and then we look at the response, and we only look at the response over the whole interval, then it doesn't matter how quickly or slowly you move along it, you get the same response. And that is wonderful, because that actually factors out an infinite dimensional group of symmetries. It's not completely wonderful, because there's still an infinite dimensional thing left. But it certainly reduces the problems. Used carefully, it can reduce the dimensionality of your problems quite dramatically. So, for example, in that psychiatry thing with moods, it changed things from needing 1,000 or so features down to needing about 50. And 50 is realistic with the data, and 1,000 is not. Let's look at an example. Suppose we consider a play, and suppose this play has happy aspects and sad aspects. We can translate this into a stream or path. We'll move in the horizontal direction when it is happy. When it is sad, we'll move in the vertical direction. The lowest degree terms in the signature will record the overall intensity of happiness and sadness. The increment between where you start, no happiness or sadness, and where you finish. The first order signature doesn't pay any attention to the order in which things happen. Let's suppose the play starts happy and finishes sad, or the other way round. The play would be quite different. A tragedy or a comedy. A tragedy and comedy will produce quite different curves, with the same overall mix of happiness and sadness. We'll see that the signatures are quite different. Here we are. The happiness and sadness are moving at more or less the same rate. The first two terms in the log signature here represent the overall mood intensity. They do not take into account order. Looking at the coefficients, we see that we move 204 units in the horizontal happiness direction and 208 in the vertical sadness direction. We have a third term, 518. This is the area between the curve and the chord from the end to the beginning. It's quite small. Now let's look and see what happens when we look at a tragedy. Happy at the beginning and sad at the end. Happy, sad. You see, the increment doesn't change very much, but we now have a huge area, a huge negative area as the third term. On the other hand, if we had a comedy, sad at the beginning and happy at the end, again, the first two coefficients don't change that much. But can you see the third term in the signature? The area is positive. This second order term strongly distinguishes the tragedy from the comedy. It starts to capture the order in which things are happening. There are two first order terms, one second order term, and there are two third order terms. These allow you to distinguish finer order structures. If a line comes first and then a hump, you'll see that these two third order terms, the first is positive and the second is negative. On the other hand, if the hump comes at the beginning and the straight line segment at the end, the third order terms are both negative. What's happening in a fairly robust top-down way, with more terms giving more information, is that one is capturing the order of the events. The early signatures from a 3 are quite robust to the way we draw the 3. The signature description is not affected by the speed or the steadiness when we transverse the video of the play or redraw the three. This symmetry killing has several real-world practical advantages. It gives fixed low-dimensional feature sets that don't care how many sample points there are. It doesn't care about missing data. It doesn't care about all sorts of things. But most interestingly, from a mathematician's point of view, describes the functions on the space of streams. The embedding, so I don't want to spend very long on this because most of you won't understand it. But the signature can be rewritten as an integral. It lives in the tensor algebra. If we take linear functionals on those signatures, then they're obviously functions on paths. But it's very easy to show, actually, because the paths are group-like, that actually when we take the product of two of these functions, we can rewrite it as a sum. In other words, we can characterize the functions on this space as the dual space of the tensor algebra, the shuffle algebra. And that actually is very practical because it says that we can use linear regression to get things. Mathematically, it's quite a hard story to show that this signature is actually telling you all you need to know. But it does, and ultimately you get tied up in some quite interesting algebra. I don't really want to go into it very long, but I do want to at least tell you that that's the case. And I think, and new PDEs, but this is more fun and more understandable. So this is going the other way. So this is just convincing you that if you know the signature, you can get back to the paths. And you'll see that it's actually recovering quite complex paths in 3 dimensions simply from these sequences of coefficients. It's a bit like a Fourier series, except that it's not. A Fourier series is a way of describing functions on the line. Signatures are a way of describing functions on paths. So it's an infinite dimensional leap by comparison. Right. Now I'd like to tell you a little bit about applications of it, because it does open doors, like I tried to explain with the integers. Once you understand there's the linkage, you can then take advantage of it to make applications. So one of the interesting things that you can do is you can try to learn, because that's what most of modern data science is about, parameterizing families and then learning. You can try and learn F. You can try and learn the relationships. This is actually very useful in healthcare and in other places, because one of the things you'd like to understand quite often is counterfactuals. You'd like to use data to allow you to predict what will happen if you do something. So you're not really trying to say what happens if something happens. You really want to know what happens hypothetically, and you want to be able to vary the input, the policy, to find the best policy. So you want to understand how to deliver cancer drugs, and you'd like to understand what would be the best policy. Then you can use data to learn the relationships between the inputs and the outputs. And then you can use the learned model to try and do something. It's not straightforward, but there's quite a lot of work in it. So one person who's contributed to write a lot to that is Michaela van der Schaar, who's now in Cambridge, but was here. And that relies on work from our team on these neural SDEs. Ensembles of paths are a different flavor. I've mentioned them before. They use expected signatures, and they turn up in all sorts of places. You can understand that they may turn up in this case, in a work of Maud Lemercier in agriculture, and you're trying to understand the growth of the wheat in different fields across the country, and you're trying to do that and learn the behavior so that you can look at what happens next year and predict the outcomes before it actually happens. And when you do all the tests, you discover that you can do it better than everybody else. But perhaps interestingly, you can take these trees and you can do the same sort of thing with these trees. Now, these trees actually came from trying to understand malware in computers. The idea is that when you have a process, this process does a few mundane things, but then it generates new processes, and then they generate new processes, and you get a tree. And by looking at those paths together, you can get an ensemble of paths. By using expected signatures and kernels, you can do something with it, and you can actually make assessments as to whether or not this was a piece of malware or not. I still think Martin would find it difficult to imagine that this object is a particular element of the tensor algebra. But actually it's done at that level of abstraction. The whole thing, in a way, that I'm trying to tell you today is that there is vastly different applications. But actually there's a level of abstraction which allows you to think about them in common. And it's not time series, because time series would have this explosion of dimensionality as you have multiple streams. But this one, and I think I'm managing my time quite well, this one I think is a bit more fun. And it was one of the relatively early things we looked at. And so it's no longer state of the art, but still I think it raises interesting points, and probably we could make something state of the art again, but these worlds move quickly. It's very easy now to download software which will take a video and turn that video into these slightly noisy skeletons. The interesting thing, though, is that can you use these skeletons to figure out what people are doing? You can probably do better if you don't use the skeleton, if you use the whole body. But the great thing about the skeleton is that it preserves privacy. And you would not want, or at least I would not want, a video of me and my house as I wander around in the morning getting my breakfast. But you might accept a video of the matchstick man, and it would tell you that you've fallen over, or whatever, or tell your family that you've fallen over. So you'll see that the matchstick men do actually contain quite a lot of information. It's not too difficult to figure out what this person is doing, is it really? I'm not going to tell you because we'll confirm it in a minute. This one may be a bit harder. And I'll show you them both in a minute. But before I do, I want to point out these are streams. They're streams in, actually there's about 15 points on these people, I think, and these points are in 2 dimensions. So actually it's a 30-dimensional path. And so it's fitting into the framework I've already been talking about. But it would be interesting and useful, I think you'd agree, to learn how to interpret those things. So that one is no surprise, right? And notice there are red skeletons and blue ones. Red ones were put on by hand and are accurate, and the blue ones are put on by these automated processes and are noisy. So there are 2 different challenges, actually. One challenge is to figure out what people are doing on the basis of the red ones, and one challenge is to figure out what people are doing on the basis of the blue ones. The latter probably being more useful in the long run. Okay? But that's no surprise. I wonder how many people guessed the next one. All right? And that, I think, raises several points. This is not a trivial game. The variety of human behavior is enormous. There are 8,000 different Chinese characters, and you get very cross if the next one is wrong, if you happen to be wanting really to write Chinese. by hand. By the way, most people don't, all right? Most people actually prefer Pinion because it's quicker, but oldies like me, except of course not me, I think are more interested in using the actual characters and the handwriting. But still quite a few millions of people have used it. Okay, so the methods using the path signature worked. I won't bore you with them. They work very well, actually. And one of the nice things that came out of it as well was that actually it gave a lot of interpretability. You could actually see which parts of the body movements you cared about most to do the different actions. So if you were catching the bit that was most important was just below the pelvis. But if you were climbing stairs, then it was these cross actions that mattered. And kicking is another one. Anyway, you can see that these sort of make sense and they're sort of fun. And if you want to play with these things, do feel free. On our website, we have an area called examples. And in that part of the website, we have numerous notebooks, Jupyter notebooks, which take you through all these different examples. For example, you can train your own action detection game. It only takes about 1.5 minutes to do a sensible training. And then you get reasonably good results. You don't get state of the art, but you get reasonably good results. And the point is that this signature stuff works on lower dimensions because it kills dimensionality. And so you can do things with relatively small data sets. There are several problems that you can state abstractly, which I think you would agree are things we really would like to know. So let me give you one or two before we go to the last slide. Suppose I have a large collection of patients, and such data sets exist actually, although we've not done the analysis. And suppose that they have been observed from, say, 50 days before a diagnosis with cancer and for 40 days afterwards. And you have this large ensemble, this collection of paths. And now somebody comes along with 50 days up to the diagnosis of cancer. Then I think it would be quite useful for that person, or at least for their clinicians, to be able to see, on the basis of evidence from people with similar experiences to them, from this £200,000 collection of people, not pound, 200,000 people collection, what are the likely events over the next 40 days for these people? You know, some people are going to come with one set of conditions that are not, they're going to predict the future, you can't. But you could give a collection of scenario paths that were reasonably representative of the future for that person, given all the evidence of what happened to everybody else, and give them some understanding of what's going to happen. But that's a generic problem. We can all understand why it might be useful in that case. But it can be useful in financial investments too. It can be useful in all sorts of things where you want to see what's likely to happen in the future from something, given the ensemble of lots of people's experience before and after. And they don't have to be people. There's lots of different situations. It's a very generic question. And actually, that question was exactly the one answered in that paper I referred to from 2013 at some abstract level. It still needs work to make it concrete and realizable. But that's the sort of question one might want to answer, and I think you can see that it's useful, and I think you can perhaps also see that you can do it without reference to the context. Another one that you can do without reference to the context is actually outliers. This turns out to be a very practical thing too. So I don't mean that a path is evolving and something funny happens. I don't mean that at all. I mean that you have a huge ensemble of paths. For For example, books written by different authors. And you'll find an example of exactly this on our website. But you have all these books, and you look at the text of them, and you'd like to recognize that you've not seen this author before. They're unusual. But actually, this is a very broad question. So you have a stream of paths, an ensemble of paths, and now you have one new path. And you'd like to give it a score, which says how far out is it from the rest of them? How much is it an outlier? This is a really interesting non-parametric question. The key to it is you shouldn't make assumptions about the behavior of the outliers or anything else. The interesting thing is that you can actually really build models doing this. They rely on the signature to vectorize the data, and then intrinsic ways of working out variances and covariances and nearest neighbors. But there are sensible approaches to doing this at that level. That is actually what we would really like to do with the cybersecurity data. We would really like to say, we've looked at all this computer stuff chugging through the machine. This doesn't look normal. You should go away and look at it and see whether it's normal or not. And you can see that this is a really basic question. But I wanted to finish off with a light, compared with cybersecurity, sort of usage of it, but not a negligible usage of it. And that is that when you look up into the stars, the signals come down, and surprise, surprise, they're noisy from time to time. People turn on their car. Actually, the key fob is meant to give off quite substantial interference. But you get lots of things. In fact, a lot of the time you can't use a telescope because of interference. Sometimes, I'm told, which surprised me, the period is even a year. But normally it's much less than that. So you'd be very interested in recognizing when is it that this signal is contaminated by interference. Well, if you have a large collection of normal data that you have successfully extracted astronomical information from, then you can use outliers. Outliers are really a good idea from this perspective because the radio frequency interference this time, there's no reason why it's going to be what you've seen before. And so you can actually use the outlier methodology we were talking about before, combined with a big corpus of good behavior, to recognize the areas where there is potential interference. You see, this picture is meant to illustrate the outlier, right? So we've got all these paths that are normal, but this one clearly isn't. And Maud and Paula, mainly Paula on this one, with Tom and me, have been working on building a proper model that can find this interference. And it matters, this interference, and there's already software out there that does it. And even against real data at the moment, but it's not a published paper, so it can all still go wrong, we seem to be doing really very well. We have a really good area under the curve, which means that we can detect very faint interference without getting a lot of noise from the data. And we seem to be more than competitive, but I emphasize the seem to be, because at this point it's still early days. But you can see, I hope, that there's a wide range of applications from health and hospitals to astronomy, and they all have potential impact. I mean, the SKA one, which is the team we're working with, is an interesting one because if we could increase the availability of astronomical data time by, say, 5%, because we were better at detecting the interference and eliminating it, well, it's worth bearing in mind that this telescope cost nearly £2 billion. So effectively, we may be increasing its value by 5%. These are not negligible things. The healthcare is not negligible, and so on. But it's very much math at the end of the day. At the end of the day, we don't think about the dollars and we don't think about the astronomy very much. We think about managing the data and packaging it and controlling the scalability of it. The big problem today, which we've really not resolved, although there are some answers, is scalability. These problems get very big very quickly. If they're too big, they're not tractable. So you need effective tools to push them down. That's it, except for one caveat I want to put in. I want to emphasize, because perhaps it's not clear from this talk, that the signature itself is not a panacea. It's a tool which, used with all the other tools of data science, can often give you an incremental improvement that's real. But it's not something you go away and use on its own. I don't want to sell it as if it's a panacea. It's not. And on that slightly down note, the good news is that I've finished, and you'd be an outlier if you weren't relieved, I suspect. But anyway, thank you very, very much indeed.